Hi everyone. Today I want to introduce our new method for dealing with the safety problem of human-robot shared autonomy. Shared autonomy provides a framework where a human and a robot jointly control the system's behavior and enable a more effective solution for various applications. The safety of shared autonomy is actually a critical problem. If the human and robot interact with each other through physical contact, safety becomes even more challenging. This is because even though a robot knows what is safe or not, the human input may still affect the safe operation of the robot. In this shared autonomy example, a manipulator robot moves its effector among some topic regions. However, the target region, which is defined by the human operator, is not directly given to the robot. The robot needs to infer the target region from the measurement of the forces exerted by the human operator onto its effector. Based on the inference, the robot effector needs to start from an initial region and move to a target region without passing through any of these red obstacle regions. To maintain a safe robot operation, we can use control barrier function method. It determines the robot input for enforcing a safe robot trajectory. But this type of method assumes we have convex state space constraints. This is not guaranteed in a lot of shared autonomy problems. For solving the non-convex trajectory planning problem, we may consider to use a sampling-based method such as the RRT method. But notice the original RRT method had no feedback control policy provided. Without a feedback control policy, it is hard to guarantee a safe execution of the desired trajectory. Especially now we're actually facing the uncertainty and external forces from the human operator. Except for all these position-based control methods, there are also force-based control methods designed for physical human-robot interaction. Some of these force-based control methods, such as the impedance control method, adjust the human dynamic uncertainty and achieve a complementary stability for the human-robot coupled systems. However, force-based methods usually consider the robot as a strict follower of the human operator and rely on the humans themselves to obey the safety constraints. Therefore, this research aims to provide a method which actively corrects the human unsafe action during the human-robot collaboration, deals with non-convex safety constraints, and provide feedback control policies which are robust to external human force inputs. Before showing our proposed method toward this research problem, I want to introduce two preliminaries. The first one is called barrier pair, which is a pair of a barrier function and a feedback control policy. When we are using this feedback control policy, the sub-level set of this barrier function becomes an invariant set. While we are inside this invariant set, the state and input constraints are both guaranteed. If we just consider a quadratic barrier function and a full state feedback controller, we will obtain ellipsoidal region of attractions, and the barrier pair synthesis problem will become a linear matrix inequality problem. Another thing I want to recall is the RT algorithm, which will be used later for dealing with the non-convex state space constraints. Here, I will only recall the three key steps of expanding the RRT graph. Sample random configuration, find the nearest point in the graph, and create a new point by expanding the nearest point toward a random configuration with a constant distance delta in each iteration. Based on the barrier pairs in RRT, we developed the barrier pair RRT method precisely. It replaces the waypoints of an RRT graph by barrier pairs. Because of that, the robot obtains feedback control policies to safely execute the trajectory from the initial region to the target region without going through any obstacle regions. Now, let me explain how the barrier pair RRT method can be extended to the safety control problem of shared autonomy. To build the barrier pairs along RRT, we need to consider the multi-body dynamics of the robot. Here is the Lagrangian equation of the robot with a joint configuration vector Q, a robot torque input vector U, and a human force input vector W. And this human force vector represents the forces exerted by the human operator onto the robot and effector. Its Cartesian workspace vector X can be considered as the output for a state space model of the robot dynamics. To create a subproblem of barrier pair synthesis, we need to linearize this robot dynamics around a predefined equilibrium point. However, this linearized robot dynamics model soon becomes invalid when the robot configuration starts to deviate from this equilibrium point. A solution to this issue is to consider a bounded state space region around the equilibrium point and calculate the norm-bound uncertainty of the robot dynamics for all states in this Z region. This process can be done by a quadratic inclusion program method. And then we will obtain a robust norm-bound linear model. So the nearby obstacles around the equilibrium point will provide us some position bounds for defining this Z region. We also need to consider the velocity bounds at each joint. And this position and velocity bounds together define the Z region for our local state space constraints. And we also need to consider the torque limit at each joint. Except for all this state space and input constraint, we also assume the external forces exerted by the human is also norm-bounded. Then we can write the position, velocity, and the robot input constraint into linear matrix inequalities. Then we need another linear matrix inequality constraint for enforcing the Lyapunov stability under the assumption of the norm-bound human force input defined in the set of W. Because of the bounded human force input, the barrier pair cannot converge to the equilibrium point precisely. Instead, they actually converge to a residual set, which is a smaller ellipsoidal region centered at the equilibrium point. The size of this residual set is decided by a predefined value epsilon 0, which appears in this Lyapunov stability constraint. The derivation of all these linear matrix inequalities can be found in the proofs and references in our paper. By considering all these linear matrix inequalities, we can create a barrier pair synthesis problem with a cost function that maximizes the volume of the ellipsoidal region of attraction. Now I can introduce the barrier pair RRT algorithm to our shared autonomy problem. If you recall the 3 steps of RRT, sample a random configuration, find the nearest point, and create a new point, barrier pair RRT has something similar. Vertices of RRT becomes barrier pairs in the BP RRT. Instead of expanding the graph with a constant distance delta, we create a new equilibrium point at the level set of the nearest barrier pair corresponding to a smaller than 0 value epsilon 1. Then we can create a new barrier pair centered at this new equilibrium point. Notice that epsilon 0 needs to be strictly lower than 1 minus epsilon 1. It will guarantee the residual set of the new barrier pair is contained by the unit level set of the nearest barrier pair. Under this consideration, we can have the robot make a transition between the 2 barrier pairs safely without going through any of the obstacles. Different from a full robot autonomy, where the target region is directly given to the robot in this problem needs to infer where the human wants to go to using the human force input measurements. Then the robot can use the barrier pair RRT to execute a trajectory toward the human target region. To infer the human's objective, we build a likelihood function based on the inner product between the human force vector and a workspace precision vector, which points to one of the possible human objective regions. Then we use a Bayesian method to update our belief about where the human operator wants to go. Then we pick the region which had the highest belief value and trigger the barrier pair sequence in the barrier pair RRT graph to execute a trajectory safely. Here, I will show you a simulation of a two-DOF manipulator, which illustrates how the human intention inference and barrier pair RRT work together for a shared autonomy scenario. The manipulator has 2 point masses located at the distal end of its 2 links. You can see some polytopic regions in its workspace. Region A1, A2, and A3 represent the task regions, which are also the possible human objectives. Region A4, A5, A6 are the obstacle regions. And we also have region A7 represents the base of this manipulator, which is also non-passable. Here are the barrier pair sequences synthesized using the barrier pair RT algorithm for this human-robot shared autonomy scenario. The smaller ellipsoids centered at those bigger ellipsoids are the residual sets. We first build the barrier pair sequences from A1 to A2, from A2 to A3, and from A3 to A1. The barrier pairs in the middle of each barrier pair sequences are defined as C3, C1, and C2. Sometimes the inference of the human's target may change in the middle way of executing these barrier pair sequences. To deal with this issue, we built 3 additional barrier pair sequences from C2 to C1, from C3 to C2, and from C1 to C3. Because of these 3 additional channels, the robot can safely switch between different barrier pair sequences if the inference of the human's objective changes. Notice that when we build the paths between 2 text regions, the third text region becomes a non-passable region in the barrier pair RRT synthesis problem. Although this is a simulation, there is actually a human operator using the keyboard to control the direction of the red human force input vector at any effector. At the top left corner, it shows the actual human objective, the inferred human objective, and the barrier pair sequence which is currently executed. Sometimes the initial guess of the human's objective is not correct, but after gathering more measurements of the human force input, the robot is able to make a new inference and safely switch to the correct barrier pair sequence. Thank you so much for listening.